not interested in any which way studying. Listen.
Notepad में मैंने
अब
बनाया
आगे आ जाओ. Come forward.
काम आया तो तूने देखा तो
Sunny, get up. Come forward. Sit forward.
नहीं सब कुछ बच्चा आ गया
Turn your.
कोई था ही नहीं वो पूछने लायक ही नहीं था पीछे आदित्यन बैठा था आदित्यन भी वो मेरे से पूछ रहा है मैं सोच रहा हूँ मैच
I'm gonna repeat again.
कुछ
What's a nucleophilic reaction? When you
हाँ मैं देखा हम ही लोग बनाते
when you have a carbon and a halogen and you have a nucleophile. Nucleophile attach the carbon, halogen leaves. What do you end up getting? CNU. What is this NU? NU is called a nucleophile. And who is leaving? The halogen is leaving as halide. This is what we are written. How does this occur? We have two mechanisms for it. What are the mechanisms called? SN1 and SN2. So, start writing. Weekend and evening batch, please continue from where we stopped. ORS2, afternoon batch, leave one page. Just want you to write one introduction that I missed, but we'll write it later. But now write down nucleophilic reactions. Please write the heading nucleophilic reactions. Nucleophilic. Write down the heading nucleophilic reactions. Nucleophilic reactions. Write down the first one, SN2. Nucleophilic reactions. Nucleophilic reaction. SN2. Online guys, can you hear me? Can you see the screen? Yes or no? One of you confirm?
Yes, ma'am. Yeah. You can see the screen.
I can't. One second. So we'll be writing two reactions, SN1 and SN2. Write down SN2 quickly, please. SN2. Nucleophilic or bimolecular nucleophilic substitution reaction. That's the heading. Bimolecular nucleophilic. Bimolecular nucleophilic. SN2 is your main heading. Under SN2, you will be writing bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution reaction. Okay. Now listen. What was the heading I told you? Main heading of today? SN1 and SN2. Now, what does this 2 stand for? First of all, you need to understand what are you discussing. You're discussing how a nucleophile replaces a halogen group. Any doubt? Now, how does this happen? Write down. Occurs in one step. Occurs in one step. First point done. Second point, keep writing along with me. What is happening, you write down. Reaction now, mechanism, you write. Then what does this 2 stand for? Any idea? What does the 2 stand for? The order or the kinetics. The step is not 1 and 2. What stands for? 2 is not for the number of steps, or 1 is not for the number of steps. So SN2 occurs in how many steps? 1 step. Write down mechanism. OH minus. Let's say you have a hydrogen, chlorine. Please understand OH minus attacks from the side opposite to the leaving group. Now, at this point, what will happen is, please draw, you will end up getting a transition state. What is a transition state? A transition state is something like this. Now, tell me, this is called, write down. Can I say, have you heard the word intermediate? Transition state is not an intermediate. Intermediates actually exist in reality. Transition state does not exist. It's an imaginary state wherein carbon is being, chlorine is leaving. Who's forming a bond? OH is forming a bond. Can I say it's pentavalent? What does pentavalent mean? It's attached to 5 things at a time. But is it true? Is a state like this possible? So it's an imaginary state. You can't actually isolate. Then what happens? Continue. Chlorine leaves, and who's replaced the chlorine? OH group and Cl minus separated out. This is the general mechanism. This entire thing happens in how many steps? It happens in 1 step. So finish till here. Done? Mechanism done? Let me take a better page. Till here, any doubts? So what did happen right now? We're starting with SN1, SN2 mechanism. The first mechanism is starting with SN2. How many steps does it occur in? It happens in 1 step. In that 1 step, can you tell me what are the 2 things that are involved? Can I say both? Write down. This is the nucleophile. This is the nucleophile and this is the substrate. Can I say both nucleophile and substrate are involved in the reaction? Yes or no? Can I say both nucleophile and substrate are involved in the reaction? Therefore, write down next point. Rate is equal to or directly proportional to both substrate and what? Nucleophile. That is why we call order 2. Therefore, the order is also 2 and molecularity is also 2. Is this clear? What does molecularity mean? Number of molecules that are reacting in a given reaction. So, this SN1, SN2 means that 2 does not stand for the steps. The 2 stood for molecularity or order. Any doubt? Is there an intermediate? No, there's no intermediate. There is only one transition state. Any doubt? And the transition state is pentavalent. Clear? Now continue writing. Now write down or reactivity of alkyl halides. Now can I say Ri, RBr, RCl, Rf? Which one will react the most? Ri. What's the reason? Shouldn't the bond between the carbon and the halogen break? Carbon iodine bond is the weakest. Why is it the weakest? It is the longest bond. Iodine is a very big atom, so this is one reason. Another important order I'm going to give you is write down methyl halide. Then we have primary alkyl halide. Give an example of a primary alkyl halide. CH3, CH2, Cl, can I say CH2Cl? Then what's an example of a secondary alkyl halide? Yeah, CCCCCl. And then you have a tertiary alkyl halide. Can you give me the order of which one will be more reactive in SN2 mechanism? Why? So I'm going to use a word called steric hindrance. मान लो, listen, who's attacking? Nucleophile. Attacking whom? The carbon. If there are big groups around carbon, will the attack be easy or difficult? Difficult, right? So what kind of groups would you prefer around the carbon? Tiny groups which are small hydrogen atoms. So what is the order of reactivity? This is the order of reactivity. Write down. Steric hindrance. Steric hindrance. I didn't even written anything. Please make it quick. Steric hindrance plays a vital role. Plays a vital role. What is the word we're using? Steric hindrance plays a vital role in reactivity of. Steric hindrance plays a vital role in reactivity of alkyl halides. As steric hindrance increases, as steric hindrance increases, as steric hindrance increases, the rate of reactivity, the rate of reactivity increases or decreases? Decreases. Keep in mind, steric hindrance is what? What does this word steric mean? Steric generally means places, as in spatial arrangement. What does the word hindrance mean? Blocking, disturbance, or so when you have big groups blocking your carbon, will the attack be easy or difficult? Difficult. So steric factor plays an important role. Any doubt? Repulsions also you can say, but here it's more of a space problem, more than electron problem. So I will just show you one diagram so that it's clear. Any doubts still here, first of all? Do we have any doubts still here? So what are the things that we're discussing now? We're discussing SN1, SN2 mechanism. How many steps does it occur in? One step. Then why is that 2 standing for? What does that 2 stand for? It stands for the order, या फिर molecularity. What is the general order of reactivity? Can I say methyl, primary, secondary, then tertiary? Any doubts here? Now, this is what I'm going to show you. Please look up. Can you see this? So if there's a primary group, there is get up. Go back. If it's a primary group, can I say there are 3 small hydrogen atoms? But when it is a tertiary methyl group, can you see that there are big, there is a carbon, that carbon is attached to hydrogen. So isn't it branching? Isn't it difficult for the reactivity? That is why what's the general order? Methyl, then primary, then secondary, then tertiary. Any doubts? Is it fine till here? Now I want you to write next point. What are the points you've written till now? We started with reaction mechanism done, rate of reactivity done. Now write down energy profile diagram. Topic under it, energy profile diagram. Energy profile diagram. You have to not take more than 2 minutes and draw it quick. Can you tell me what is this energy profile diagram? Where does reactant stand? What does R stand for? Reactant. What does P stand for? Product. What is this peak? This peak is TS. What is TS? Transition state. In kinetics, I don't know if you remember, I've told you, number of peaks represent number of steps. That one peak means how many steps are there? One step. Any doubt? In that step, since both nucleophile and the substrate are involved, it is a bimolecular reaction. Why is it SN2? The 2 is not for the steps, it is for the order, kinetics. Please make it quick. What does E stand for on the y-axis? Energy. What does X stand for? Reaction coordinate. What is the other word apart from reaction coordinate I can use? Progress of the reaction. You have to make it a little faster today. We don't have much of time. So please write along with me. Any doubts till now? So we started with SN2, nucleophilic substitution bimolecular. Step 2 has nothing to do with the number of steps. Step 2 has to do with the kinetics or order. Since the nucleophile and the substrate are involved, it is a bimolecular reaction, or molecularity is 2, order is 2. Anybody has any doubts, please put up your hands. Who has any doubts? Weekend, evening, online days, is it clear now? Alton, can you hear me now?
Yes, ma'am, we can hear you.
Any doubts still here? Okay. Now write down. Yes, Samrit.
The order is always 2.
Order is 2 in this case. SN2, yes. It depends on the substrate, which is your alkyl halide and the nucleophile. Is it fine?
Yeah.
Now write down solvent. Solvent, you have to wait for me to finish SN1 also, but I'll just make you write here so that we have an idea. Write down solvent. Under which mechanism are we still dealing with? SN2. Write down solvent. Now, aprotic polar solvents are preferred. You write down what this is, then I'll give you an entire note on explaining what this means. Aprotic polar solvents. Aprotic polar solvents are preferred. Please write down what these are, then I'll explain. DMSO, example, DMSO, DMF, etc. DMSO, DMF, etc. So we are done with anything we missed out. General scheme done, reactivity done, order of reactivity done, energy profile diagram done, solvent done. There's something called configuration part which we will discuss later. Next heading, write down SN1 mechanism. What do you think this will be? What's the full form? Unimolecular. N stands for nucleophilic. S stands for substitution. Unimolecular nucleophilic substitution is what is SN1 mechanism. Any doubt? SN2 is bimolecular. SN1 is unimolecular. SN2 was how many steps? One step. SN2 was one step. SN1 is how many steps? Write down. Carried out in how many steps? 2 steps. That's the first point. Write down. Carried out in 2 steps. Write down the first mechanism. I want you to draw the entire energy profile for steps. Step 1. Step 1. Step 1. Let's say you have a halogen and you have Me groups. What does Me groups mean? Methyl groups. CH3 groups can be written as Me groups. The first step here is there is literally no nucleophile appearing. And what is the first step? The first step is halogen leaving. If your halogen leaves, what do you end up getting? You end up getting a carbon with a positive charge. You end up getting a carbon with a positive charge and X minus. This is called an intermediate. Do we know what's the difference between a transition state and an intermediate? Intermediate can actually exist and you can isolate them. A transition state, on the other hand, does not exist. That is the difference. Intermediate can exist, but a transition state cannot exist. Now, what sort of an intermediate is this? Can I say correct? It is carbocation. What is carbocation? A positive charge on the carbon is what we call as carbocation. C plus. Any doubts? Now, this is also my RDS. Now, if you give me a full form of RDS, rate determining step. Your rate determining step is your slowest step. And which is your slowest step here? The first step. What is the first step? Also called as RDS. Any doubt? So what is step 1? Write down. Formation of intermediate. Formation of intermediate is my first step. Formation of intermediate is my first step. Write down step 2. Write down step 2. Now who should attack? The incoming nucleophile should attack. Now in the carbocation now, the attack of the nucleophile happens and you will attack onto the carbon. And what do you end up getting? C and U with 3 methyl groups. What does this NU stand for? Nucleophile, any sort of nucleophile. So first step is the formation of the carbocation. Your carbocation is the intermediate. Second step is the attack of the nucleophile. Next, write down. Third point. Rate is directly proportional to. It only depends upon substrate. Can you tell me why not on the nucleophile? Yeah, so I have told you multiple times in kinetics also. The slowest step is the one which is the rate determining step, and rate determining step controls your order. In your rate determining step, was the nucleophile even included? No. So rate will only depend upon what? Substrate. Okay, so write down that. Now write down. So what is the order here? Order is 1. Why is the order 1? Because it only depends upon the substrate. What do you think? What is the molecularity? All of you write down. Molecularity also equal to 1. Order is 1, molecularity is 1. Why only 1? Is there a nucleophile? Yes, there is. But in the rate determining step, only the substrate is involved. Any doubts? Is it clear? So how many reactions? How many points? The main thing done, mechanism done. Write down now. Leaving group order. Write down leaving group order. Okay. Leaving group order. Now, what do I mean by a leaving group order is what we wrote in the previous. Sorry? What is leaving group order? Let's say I have RI, RCR. Assume R is the same. Which will react the fastest? Still RI, RCR, RCR only. Why is that? Because the leaving group, you have to check the size of the halogen atom. So this order still remains the same. Now I want you to write reactivity of substrate. Write down, this is a little important. Reactivity of substrate. Now write down, in essence, since carbocation is the intermediate, the reactivity of the substrate, the reactivity of the substrate, is directly proportional to the reactivity of the substrate is directly proportional to the stability of the carbocation. So what I'm trying to tell you is, since intermediate is involved here, higher the stability. See, let's say I'm walking from here to here. If only I have a purpose, will I walk? So any reaction is carried out with the purpose. If a carbocation is formed, only if the carbocation is stable, the rate of reactivity will be higher. Are you understanding? So if intermediate is not stable, will the reaction want to occur? No. So now tell me, among the carbocations, is primary, secondary, or tertiary more stable? So write down order of reactivity there for tertiary alkyl halide. I'll show you why. Will occur, yeah. So tertiary alkyl halide is stable than a secondary alkyl halide, which is stable than a primary alkyl halide, which is more stable than a methyl alkyl halide. Please join on time. I said this will be the last weekend class extra for all of you. I'm not going to call again. But please join on time. When I say 3:40, joining at about 4:10 after half an hour of the class you will not understand anything. Now, what is the tertiary alkyl halide? Why is tertiary alkyl halide more stable than? Why is the tertiary alkyl halide more stable? Maybe Virkamai, please.
Yes, Eric.
Maybe mute your mic. A tertiary alkyl halide, then you have a secondary alkyl halide, which is more stable than a primary alkyl halide, which will be more stable than a methyl alkyl halide. Why? Why is tertiary more stable? Very good. So there are plus I effect. Also, there's another reason. Hyperconjugation. Very good. So there is plus I effect of alkyl group. There is plus I effect. What does plus I mean? All of you write down. What does EDG mean? Electron donating groups. So methyl group is a donating group, which shows plus I and EDG. Therefore, plus I effect stabilize it. Also, what's the other reason? Hyperconjugation. How many alpha hydrogens or how many alpha carbons if I ask you? In the first case, 3 alpha carbons. How many alpha hydrogens? 9 alpha hydrogens. Count these. How many alpha hydrogens here? 6 alpha hydrogens. How many here? 3 alpha hydrogens. Greater the number of methyl groups, greater is the hyperconjugation structures. This heading comes under hyperconjugative. Greater the hyperconjugative structure, greater is the stability. Any doubt? So, in short, if I ask you again, what is the order for primary SN2 mechanism? SN2 is methyl, primary, secondary, tertiary. For SN1, what is the mechanism? Tertiary greater than, which is secondary, then primary, then methyl. Any doubt? Is it clear? Now, in energy profile diagram, how many peaks should be there? 2 peaks. Why should there be 2 peaks? Because there are 2 steps. And this peaky region with this one small gap that you see, that will be your intermediate. Any doubt? In kinetics, I have discussed the peaks are always going to be transition states. The groove, the small dip is what we represent the intermediate. How many steps are there? That many peaks you will end up getting. Any doubt? Next heading is energy profile diagram. Next heading is energy profile diagram. Showing more amount of energy. Yes, they are showing more amount of energy as compared to reactant and product. No, but transition state is even worse. Intermediates are unstable. That's why they have a higher energy. Lower energy only as compared to TS1 and TS2. What does TS stand for? Transition state. Which step has compared to reactor and product? Have they high or low? High. They're unstable. So please write down. Can you see again? I'll just explain once. What is E on the y-axis? What does reaction coordinate mean? The progress of the reaction. Can you see two peaks? What does this groove represent? Intermediate. Can you tell me what do you think is the first transition state and the second transition state? What do you mean? First transition state will be leaving of the nucleophile. Second transition state will be leaving of the halogen. Second transition state will be where the nucleophile tries to attack your carbon. Therefore, you end up getting two transition states. Any doubts? I'm going to repeat again. SN1 mechanism has two steps, two peaks. SN2 mechanism had one step, one peak. That's it. The peaks always represent transition state. The grooves always represent intermediate. After this, we'll not write for some time. Don't waste my time. I hardly have 1.5 hours. So, shut up. Now, I have to finish one topic. Now, that one topic, I do not want as writing. I will explain for me NCRT and my notes. I'm going to be sending you both of these notes today. Hello, I can I will not send because I'm making it right. Isomerism part, I will send you. Done till here? Now write down solvent. One more topic, start reading with the start point. Solvent. SN2 mechanism favored with solvent. Aprotic. So SN1 favors write down polar protic solvent. Under solvent, write down the solvent preferred is polar protic solvent. Example, please give me an example of polar protic. You've heard of anywhere. Write down water, H2O, methanol. Write down under solvents. Under solvents, what is the solvent we are preferring? Write down polar protic solvent. What do you think is the order going to be? Write down polar protic. What do you prefer? Example, water, methanol. What is methanol? CH3OH. What is ethanol? C2H5OH. Now I come to what is this word polar protic, polar aprotic, all of that. First, listen to me. What is the whole point of a solvent? One is it should provide a medium. Second thing I need is there are two types. The two types, don't write, listen, polar and non-polar. Do you remember polar, non-polar dipole moment? So dipole moment is something called as mu net. If the net dipole moment is 0, it's called non-polar. Examples of few non-polar are your benzene, CCl4, etc. Under polar, we can have two types. So the two types we can have polar protic and polar aprotic. Is this difference clear? If they have some dipole moment, they come under polar. What does the word protic mean? If they have hydrogens, they are capable of forming hydrogen bonding, then they are called polar protic. If they are not capable of forming hydrogen bonding, they are called polar aprotic. Any doubts here? Now for SN2 mechanism, or let me say it. SN1 mechanism, which one did we require? Polar protic. Why? So that if there is something like water, it can stabilize your intermediate. Whereas for SN2 mechanism, what do you require? Polar aprotic. Now write down a heading, solvent, Now write down the heading solvents. Start from here, please. Polar solvent, non-polar solvent. Under polar, polar protein, polar protein. Non-polar में carbon disulfide, CCl4, benzene. Let's be a little faster, please. Can you give me the order once again? For SN2, what is the reactivity order? Primary, secondary, tertiary, or methyl primary, secondary, tertiary. For SN1 mechanism, tertiary greater than secondary, then primary, then methyl. Now DMF, DMSO are few terms. Nobody is asking you to know the structure. It is just for your understanding. DMF stands for dimethyl formamide. DMSO stands for dimethyl sulfoxide. And there is one more thing. What is PHF? Tetrahydrofurane. These are a few solvents that we frequently keep using. These are a few solvents. This comes under which category? Polar A protein. Acetone diethyl, that's oxygen, that's an oxygen in the center. Diethyl ether. DMSO, DMF, and THF. What is THF? Tetrahydrofurane. Done? Please make it quick. You don't have to know the structures at all. Just that going forward, if I say DMS, DMSO, you should have an idea. That's about it. Next. Now we're discussing a very, very important topic and you will write along with me. Do we know what is benzylic and allylic halide? Okay. Please draw allylic halide, all of you. Allylic halide. You can write this coming thing as a note point up to you. I want you all of you to write allylic halide. Online also, please. Allylic. It's a new thing. I brought up. You should do the structure. You should draw the structure and I'll correct you. Type in that combination. Or amide. FORM. Allylic halide. तूने लिखा है स्ट्रक्चर बना स्पेलिंग तो सब आती है वेरी गुड वेरी गुड नो दैट इज विनाइलिक विनाइलिक This is very disappointing. What is allylic halide? Oh, the CH. It is attached to sp3 carbon, which is then attached to sp2. How are you all not understanding what allylic is yet? Allylic looks something like this. Please write down. CH2 double bond. No, basic on this one. CH2Cl. Now tell me, is this primary, secondary, or tertiary? Primary. Would you prefer it to undergo SN1 or SN2 generally according to the order I gave you? And according to the order I gave you, should be SN2. But write it down. Favors SN1. Can you please write? Because what's the first step in SN1 mechanism? Formation of the carbocation. What carbocation will this form? It is allylic only, but write down this is called allylic. This is called allylic carbocation. You know why is this one of the most stable carbocations? Why? One word you have. Resonance. Good. It's stabilized via resonance right now. Stabilized via resonance. Now, how will I draw the resonating structure? Please write down along with me quickly. CH2 double bond CH CH2 plus. How will the resonating structure be drawn? This will go like this. And canonical structure, this will go CH2 plus here. CH double bond CH2. Isn't this resonating structures? That is why allylic carbocation is extremely stable. What is the order? Why? So that is why. See, I told you, more the stability of the carbocation, it will want to prefer which mechanism? SN1. So even though it is a primary allylic structure, but you also have to check it's very stable carbocation, therefore favors which mechanism? SN1. Online, any doubts till here? Next, write down. Note under note only benzylic halide. All of you draw benzylic halide and show me please quickly. Benzylic halide. What is benzylic halide? CH2X. Halogen is attached to a carbon, which is then attached to another carbon. This is also primary, but it could also undergo which mechanism? SN1. Why SN1? Because same thing again. Just like allylic carbocation is stable, this is something called as benzylic carbocation. Why is benzylic carbocation stable? Same thing, stabilized via resonance. Now we'll draw the resonating structures quickly. Please make it quick. Stabilized via resonance. Now how will this resonating structures look? So if you have, let's say, a CH2 plus. Is carbocation electron rich or deficient? Deficient. It has a positive charge, which means it will pull electron from the benzene. Please draw the resonating structures quickly. Double bond CH2 plus charge here, bond bond. Double bond here again. You will end up getting a positive charge here. Two bonds. Double bond CH2. Bond will take the position. By now, at least resonating structures you should know, guys. Bond and then bond, double bond CH2. This will come back here and you end up getting resonating structures. So why are benzylic and allylic carbocations extremely stable? Because they are stabilized via resonance, and you will therefore know that they would rather undergo SN1 mechanism. Any doubt? Electrons are moving. CH2 is electron deficient. So who will pull the electron? Benzene will pull the electron. When benzene electrons will go towards CH2, you will end up getting a positive charge. Then which one? CH2 plus, meaning it has lost a bond. So it would rather gain electrons rather than losing. So it is pulling electron from the benzene ring. Any doubts? Yes, no. Now, how many carbocations we've learned? This is little bit of 11th, but I'm discussing here again. Do we remember ABC? I've given you an order, CBA. No, nothing is striking you. Tertiary butyl carbocation, allylic, benzylic. Among them, write down. Next note point. Stability of carbocation में instability of carbocation, I want you to remember the order C greater than B greater than A. This is the order I want you to remember. C greater than B greater than A. CDA. Now what is the C? This is a trick I use. You can use CDA. मतलब क्या है? Tertiary butyl carbocation is extremely more stable than what is B stand for? Benzylic carbocation, which is more stable than allylic carbocation. So remember this order of reactivity. This is third butyl carbocation, normal carbocation. That's why I'm using C. Third butyl carbocation, CCC. This is my benzylic carbocation, and this is allylic. SN1 mechanism done, SN2 mechanism done. Now we're slightly moving on to a topic called stereochemistry. What's the topic? Stereochemistry. Stereochemistry notes will be sent to you. Questions you will be writing, then we will continue the chapter. Okay? Notes you will be sent to you only for stereoisomerism. The rest of it you have to write. After this topic is done, put your pens down, just listen to me. Online guys also, please listen to me carefully. This is coordination chemistry also I discussed. I've discussed this in coordination chemistry also. What I'm trying to say is, certain compounds are optically active. The remaining few compounds are optically inactive. What is this optical active inactive topic? Now listen to me carefully. What exactly happens is, normal light or ordinary light has wavelengths in all directions. I am using a Nicol prism and converting into PPL light. What is PPL light? Plain polarized light. All of you listen now, stop writing, nothing to be written. I'll explain and send you notes. If you have ordinary light, this is how ordinary light will look. On passing it through something, I'll end up getting, what light is this? PPL light. This PPL light, if I pass it through my organic sample, three outcomes are there. How many outcomes? Three outcomes. First outcome is, the light will still come out as it is without any rotation. It will come like this. These such compounds which cannot rotate the light are called optically inactive. If my compound is capable of rotating light to the right, then I say it's optically active. Such compounds are called D form or plus. What is this D or plus? Dextrorotatory, and plus means rotating it to the right. Third outcome is I can rotate the light to the left. Such compounds are also called optically active, and they are called L form or minus, which means levorotatory. So experimentally, what is the definition of an optically active compound? A compound which can rotate the plane polarized light is called as optical active. A compound which cannot rotate the plane polarized light are called optically inactive. Any doubts here? But is it possible for you and me to sit and do the experiment for each and every compound? Then people came up with theories saying that a compound is only optically active if it lacks symmetry or technically asymmetry. A compound is only optically active. It does not have if it does not have any symmetry. What is the symmetry I'm talking about? There are two words you will be using: COS and POS. COS is very easy. POS is very easy to understand. Plane of symmetry. For example, I have a box. Can I divide this into two equal halves? Square. No, I don't have a square. Can I divide this into two equal halves? So these lines are called what? POS. Plane of symmetry. Such a compound will be optically active or inactive? Inactive. Are you understanding? Whereas there's another thing called center of symmetry. What is center of symmetry? If I get this at the same direction, other side, if I move this atom here from here and move it to the other direction, that is two things I'm exchanging. If they still look the same, then that's called center of symmetry. It doesn't generally be asked, but for us, every time plane of symmetry is useful. If compounds have either POS or COS, then they are called optically inactive. Any doubt? Atoms. I'll show you that on more position. See, PCOS, I'll show you. Give me a minute. Now look here. I'm going to take this letters and discuss. Does A have a symmetry? Yes or no? Active or inactive? Inactive. Any doubt? Let's say P. Is there a symmetry? Optically active or inactive? Active. Any doubts? So this is how people initially started classifying. Now in your textbook, I don't know if you've seen your palm in the textbook, in the side of your textbook. Now they used a word. I'm going to now introduce a lot of new words today. First word. What was the first word we used? Optical active and optical inactive. Under optical active, what are the two things we can have? Dextrorotatory and levorotatory. If a compound is rotating the PPL light to the right, it's called dextrorotatory. If the compound is rotating the PPL light to the left, they are called levorotatory. Any doubt? Now, such compounds, which one rotates to the right and the other rotates to the left, are called isomers. What isomers? Optical isomers. And I'm going to use a word. What is the word? Enantiomers. Please by heart, what's the word? Enantiomers. What qualifies as enantiomer? Now look at your palm. The mirror image of your palm, of your right hand palm is your left palm. Yes or no? Are they superimposable? Don't do this namaste. It's not this. Lift, place. Are you understanding? Lift and place. Are they superimposable? Yeah. Not this. This and this. Are they superimposable? Does your thumb fall on your thumb? Little finger fall on your little finger? No. Compounds which are, now enantiomers ka definitions are, listen, optically active. Listen carefully. What are enantiomers? Optically active, mirror images of each other. Optically active, mirror images of each other, which are, should it be superimposable or non-superimposable? Which are non-superimposable on each other. Any doubt? Such compounds are called enantiomers. And your palm, can I call them enantiomers? Yes, because they are mirror images of each other. But are they superimposable? No. So optically active. So one isomer, so let's say one palm. Your right palm, let's call it dextrorotatory. Your left palm will be levorotatory. Any doubt? One more thing. Again, how do I check this? I can say that a compound is said to be optically active at least if there is one and optically active compound is called chiral compound. I told you a lot of words I will be using. What's the first word I used today? Enantiomers. What are enantiomers? Optically active compounds which are non-superimposable mirror images of each other. Now, what does the word chiral mean? Chiral compounds are compounds which are optically active. Now, how do you check by looking at the molecule? Because I said, no, you can't do performance, you can't do an experiment every time. So, it said that if there is a carbon with 4 different groups, I saw it. A, B, C, and D. If there is a carbon, please do this. Look here. When it comes, you let me know. Look at the code. Can you see see a carbon with 4 different groups here? What are the 4 different groups? Can I say A, B, C, D? 4 different groups. No, let's say some A, some B, some C, some D. If I draw the mirror image of it, how will it look? A, B, C, and D. Are they superimposable? Do not fold your book. What should you do? Pick up and place. Will it be superimposable? Yes or no? No. Which means they are enantiomers and the compounds are said to be chiral. So how do you check whether a compound is optically active or not? At least or minimum there should be one carbon atom containing all 4 groups to be different. Any doubts? What are enantiomers? Optically active isomers which are mirror images of each other, or we just say which are non-superimposable mirror images of each other. But what is two condition is important? They should be mirror images and they should be not superimposable. Any doubts? Online, any doubts? Take out your books, please, all of you. My simple questions we will do, then we continue with our discussion. Open your notebooks quickly. Okay, I didn't tell you, why are we discussing this? Because we're connected to which two mechanisms? SN1 and SN2. But to know about that, we need to understand a little bit of information. No? Another question, please. Write down the entire question and draw it as it is. See, questions I wanted in the notebooks. I'll wait for you to complete. Please write down.
दोनों समझो अपना अपना ब्रदर बन अब मेरे को यहाँ का बड़ा होने का मैं बोल
Identify chiral and achiral molecules. Again, tell me what does chiral mean? Optically active compounds are called chiral. Optically inactive compounds are called achiral. Chiral compound can exist as dextro and levorotatory. Second thing I need you to understand is you first drop and then hit me out. So can you do the performance experiment each and every time? No. So you have to check for a carbon containing 4 different groups. So please check. And when you find a chiral carbon, can you put a star mark? First compound, 1 and 2 में who's chiral? Guys, this is one example. This is second example. Third one. Among these 1, 2, 1, 2, 1, 2, there is one chiral, but is one achiral. Can you tell me in 1 and 2 which is achiral, which is chiral? First one, isn't it chiral? Why? Because they have attached to 4 different. On the other hand, why is this achiral? Because they are 2 bromine atoms, similar atoms. Any doubt? Only the girls are replying. Have you all slept at the back? Answer. In the second one, which is chiral, which is achiral? First one is again chiral. Any one carbon you spot, isn't this carbon chiral? Why? attached to OH group, H group, methyl group, an entire group. In the second one, is there a chiral? Why is second one